All right, so in this set of slides, we're going to go over how to take matrices that might be in parallel and combine them so we can make a combined operation that operates on multiple qubits. So we've looked at this. This is kind of just a little bit of a review of what we've already talked about in class about combining two qubits. So you can use bracket notation and FOIL in order to take two qubits. We have qubit 1 and qubit 2, and we're just going to apply FOIL. So first, outside, inside, last, in order to expand that out to a 2-qubit representation of these two individual qubits. So this operation, we can also describe it as a tensor product. So let's look at that. We've also described tensor product with vectors in class already, but just to review before we jump into matrices. If we have a circuit, so here we have qubit 0 and qubit 1, we're going to go ahead and combine their representation. So we're going to take that tensor product operation and put it in between qubit 0 and qubit 1. So we'll have our two qubits expressed, and very similar to our FOIL expansion, except now we're going to use our vector representation. We're going to go ahead and take every element of our first matrix and use that as a coefficient times the second matrix. So we'll have A0 that will multiply by B0, A0 times B1. So that's going to create the top elements of our vector. And then we're going to take A1 times it by B0, and then A1 times B1. So basically the mechanics of a tensor product operation is we take every element here and we expand it by the second operand to expand out our final vector. So we're going to get a vector that expands in size and is larger than our original two operands. So let's look at two qubits as vectors once again. So this time we'll give values to those qubits. So we've seen a little bit of this in class already, and you can see that if we take two qubits, we take their tensor product, we expand it into our vector notation. So two element vectors combined with a tensor product will create a 4-element vector. And we also have the bracket notation here. So a couple of notes about vector tensor product, because a lot of these notes expand to the matrix implementation of this operation. Qubits are combined top down, left, right with tensor product. So let's say we have the circuit here. We're going to combine top down, left, right. So top down, left, right. There's a little bit of notation that you see sometimes, or there's some common notation that you'll see in quantum text. And that often includes dropping the tensor product symbol. So this times with a circle around it. So if you see a tensor product expressed in the following way, so we have qubit 0, tensor qubit 1, you can see it written like this sometimes, where you just drop that tensor, and that simply means we just go ahead and combine those two qubits in the following way. So these are all equivalent representations, but depending on where you look, your notation might be slightly different. So additional notes, when you're working with n qubits, your vector will be of length 2 to the n. Why is that? It's because we're working with qubits, and qubits have two basis states, so that cat 0 and cat 1. And since we can be in a superposition of those both, we have to include both of those in our representation for a qubit. So if we're working with 1 qubit, we have a length of 2 in our vector. If we're working with 2 qubits, length of 4, so on. So a helpful tip whenever you're trying to quickly come up with the vector representation for a set of qubits is that the decimal value of qubits, so this is going back to our binary encoded decimal, if we work with the decimal value of the qubits in a basis state, that corresponds to the location or the index of the 1 in your vector notation. So this is for basis states. So let's try that out. So if we have cat 0, 0, and we're trying to discover what that would look like in vector notation, well, we know that 0, 0 is equal to 0 in decimal, and the 1 is placed at the 0 index. Let's try that again with 1, 1. That corresponds to a decimal value of 3. Our 1 corresponds to the 3 index. And when we're indexing where we start with 0 first. So I know sometimes there's a little bit of a a decision there of whether you start indexing at 0 or 1, but here we are starting indexing at 0. So a little bit larger example, if we have 1, 0, 1, that is equal to 5 in decimal, and your 1 will go into the 5 position, so 0, 1, 2, 3, 4, 5, and your corresponding vector notation. So that's just a helpful tip that you can use to expand out your vector representation for your qubits. So generally, the tensor product operation is non-commutative, non-commutative. So commutative property basically says that the ordering of operations is important. You can't switch the order of your operations and have the operation be the same thing. So an example of that would be 3 plus 4 is equal to 4 plus 3. So here we can switch the order of our operations or the order of our operands, and we have the same answer. That's not the case with tensor product. So if we have A tensor B, that is not equivalent to B tensor A in general. There are some exceptions, of course, but in general. So let's check that out. So if we have ket 0 tensor ket 1 and ket 1 tensor ket 0, we can see we get two different results. So this just goes and shows that the tensor product is non-commutative whenever you're thinking of those operands. So let's think about operations on multiple qubits. So previously we've discussed single qubit gates and multiple qubit gates, but as circuits become more complex, that also extends to the matrix becoming more complex. We have a combination of single qubit operations and multi-qubit operations, and we have to make them all be able to be expressed as one. So we can come up with the overall transfer function or the overall matrix that operates on a set of qubits at a given moment of time in that circuit. So once again, we can apply tensor product in order to group parallel operations, just like we would use the tensor product to group parallel qubits. So let's look at an example here. So we have a NOT operation, two NOT operations, and a swap operation. So the swap operation already has 2 qubits that it uses, but these are 2 single qubit operations, and we have a single qubit operation here. So how would we come up with the ways to describe the overall transformation that occurs during group 1, group 2, and group 3 within the circuit? Well, first we need to go ahead and introduce the identity gate. We've already talked about the identity gate, but it's worth bringing up again because it's very important for tensor product of operations. So the identity gate does not change qubit state. The output is exactly the same as the input. And on a quantum circuit, when you see a wire, that is equivalent to the identity operation. So these are both examples of identity operations. So you can actually see a symbol appear, or you could just see a wire, same thing. It's being operated on by the identity operation. And this is the corresponding matrix. So identity matrix corresponds to the identity operation. And then here we have the output is equal to the input. So we can see that qubit 0 passes through unchanged when we look at the identity operation. So let's see that in action. The qubit value here will have alpha 0, alpha 1 as its vector notation. And we do our matrix vector multiplication to see how a state evolves. And we can see that when we do our multiplication, so we have alpha 0 times 1, alpha 1 times 0 to get our first element. Well, that's just alpha 0. Alpha 0 times 0, alpha 1 times 1, alpha 1. So we can see that our state transformation result is that we get an output equivalent to our original input. So let's dive into tensor product with matrices. So we can find the overall qubit operation to transform qubits. And once again, we follow the rules for top down, left, right when we're applying the tensor product for a group of operations. So let's check this out. We're going to start here with our group 1. So group 1 is the NOT tensor identity. Then we have group 2, which is NOT tensor NOT. And then group 3 is a swap operation. We don't have to do anything here because it already includes 2 qubits. So we're good to go with that. But these two groups, we need to apply the tensor product in order to expand the operation, so it includes both qubits. So let's look at the calculation for tensor product. So if we have two gates, G0 and G1, these are on parallel, we're going to have to implement the operation of G0 tensor G1. So this operation is going to look very similar to what we saw with vector matrix, or with matrix vector multiplication, except we have a couple more steps because we have a couple more elements in our resulting matrix. So each element of the first matrix is multiplied by all the elements of the second matrix to form a submatrix, and that submatrix is used in combination with all the other ones to create a final matrix. So gates transforming n qubits are represented with a matrix of size 2 to the n by 2 to the n. So that's something very important. If you're transforming n qubits, because qubits have two basis states, our matrix representation for that gate is going to be 2 to the n by 2 to the n. So here we can see that we have alpha, tensor, there are G0, tensor, G1. So we're going to take this first element and multiply it by all the elements of this second matrix to create this first submatrix. So alpha 0 times beta 0, alpha 0 times beta 1, alpha 0 times beta 2, alpha 0 times beta 3. And we repeat for all of the elements. So alpha 1, alpha 0, or alpha 1 times beta 0, beta 1, beta 2, beta 3. Alpha 2 times beta 0, beta 1, beta 2, beta 3. And finally, alpha 3 times beta 0, beta 1, beta 2, beta 3. So essentially what's happening here when you're combining matrix, when you're taking two matrices and combining them with tensor product, is you're taking this second matrix, repeating it in every submatrix of your result, and then multiplying it, and that coefficient comes from your first matrix. So we have alpha 0 applied in this submatrix, alpha 1 applied in this submatrix, alpha 2 applied in this submatrix, and alpha 3 applied in this submatrix. So let's combine the operations in group 1 of our sample matrix, or our sample quantum circuit. So group 1 includes a NOT gate and identity operation. Since we're looking just at a wire, that's stands for an identity. So we have our NOT operation matrix and then our identity operation matrix. And we'll go ahead and expand that out. So we have every element in this top submatrix is going to use the top left element of our NOT operation. So we have 0, 0, 0, 0 multiplied by every element in our second matrix. So 1, 0, 1, 0. And then we go through and fill out the matrix for every part, or we go out and fill the matrix with those types of multiplications. So 1, 1, 1, 1 stemming from this element of the NOT operation. And then the other operand in this submatrix would be the elements from the identity matrix. So 1, 0, 1, 0. So we continue to fill out the elements for the resulting matrix for the combined NOT and identity operation. And then when we solve all of these, we end up getting the following matrix. So this would be the matrix, the result that represents the transformation on NOT, the top qubit, and then an identity operation on that second qubit. So let's check the group 1 matrix. So if we see that we have a NOT operation on the top qubit and an identity operation on the bottom qubit, we want to confirm that an input of 1, 1 produces our intended output of 0, 1. So if we have 1, 1 that passes through, our top qubit should become a 0. And that's what we expect when we have a NOT operation on that top qubit. So we have a 1, 1, we expect a 0, 1. Let's try that out with our matrix vector multiplication. So this is the matrix we just calculated. We're going to multiply it by our 1, 1 input. So this corresponds to the following vector notation. And then when we implement that multiplication, we can see that we result in 0, 1, 0, 0 for the vector notation of our result. And we know that this bracket notation is equivalent to this vector notation for this quantum state. So we confirmed that our tensor product operation to combine not and identity did result in the correct transformation matrix for this portion of our sample circuit for group 1. So let's talk about the multi-qubit Hadamard transform. This is something you'll commonly see in quantum algorithms because step 1 is usually to put all qubits in superposition. So we have a standard notation that's often used to indicate this type of operation where you tensor multiple Hadamard operations to create a state that puts a bunch of qubits into a state of superposition. So take note of this little representation here, this commonly used notation where we have H representing our Hadamard operation raised to the tensor n. So that implies a tensor product operation to scale the Hadamard to n qubits. And that simply allows us to take a grouping of parallel Hadamard operations and combine them with tensor. So let's look at that. So we have H raised tensor 2. We'll have 2 Hadamard operations that we're combining in order to create a composite transformation matrix for these 2 qubits. And that equals the following if you go through and do your matrix multiplication. We can kind of go ahead and check this out because if you multiply, one thing to note for tensor product, if you have coefficients outside of your matrix, you can just kind of pull them out, multiply them together, and put them as a coefficient of your result. So 1 square root of 2, 1 square root of 2, multiply those together, 1 over 2. Put that as a coefficient to your resulting matrix. And then if we look at our tensor product of these 2 matrices to create the final expanded composite H operation on 2 qubits, we can see that if we have 1 times this entire matrix, we get the elements you would expect. We would get all this submatrix is equal to the matrix elements here. 1 times this times all the elements in this second operand creates the Hadamard elements. We have the Hadamard elements here. And then here, since we have a -1 times all of these elements in the second Hadamard operand, we get the sign flip appear on all of these elements in this last submatrix. So that's just something to note. That's a pattern you'll see whenever you expand the Hadamard operation, that flipping of the sign, because you have that one negative element within the Hadamard operation. So to take away, we can build more complex quantum circuits by combining gates in parallel. So just like we combine qubits, we can combine their operations as well. So we apply tensor product to combine vectors and matrices. And as some notes, when we the result of a vector, the resulting vector notation for n qubits will be length 2 to the n. So this will expand out and the result will be of 2n. And then resulting matrix for n qubits will be of length, or will be of dimension 2n to 2n. So when we combine two matrix or 2 quantum matrices, we can see that they expands out to 2n to 2n as the final dimensions of that matrix or of that tensor product.